Very good evening, dear students. So, in today's class, we are going to talk about the network synthesis of LC networks. And for LC networks, a special forms of LC network, that is your Cauer forms. Okay. And in the previous class, we had talked about Foster forms of LC network for network synthesis. So today our discussion includes Cauer forms. In fact, in the previous class also, I had briefly talked about Cauer forms. So we have two Cauer forms, Cauer 1 and Cauer 2 on the lines as we had discussed Foster 1 and Foster 2. Though the structure of the network is a bit different from your Foster forms, and moreover, the procedure of synthesizing the network for Cauer forms of LC network is also uh, totally different from Foster forms. So you need to look into that carefully. And if you have completely understood Foster forms, then it will be very easy job for us to understand Cauer forms. So I have included separate examples also for each of the Cauer forms. So I hope you will be able to understand that in a better manner. So these are the books, as I have already told you. So this is your LC network synthesis for your Cauer forms. Okay. So as I told you, we have two forms of Cauers, that is Cauer 1 form and your Cauer 2 form. So students, one thing you should understand here, that Cauer forms gives us ladder network. The LC network that we will be synthesizing here, those networks will be of the form ladder. Okay. So you can see in the slide that the two networks, they look like a ladder that we have in our homes or offices, or for other purpose we use ladders. So those kind of networks, they are called as ladder networks. So you should remember this thing, that your Cauer's canonic form represent the ladder type electric networks. Okay. So here first let us have a look at Cauer 1 form of LC network. So in Cauer 1, what we will have? We will have L1, then C2, then L3, then C4, and so on. Okay. And in Cauer 2 form of LC network, your L and C will be interchanged. So you can see here that instead of inductor we have a capacitor, then instead of capacitor we have an inductor. So in Cauer form, what we can say, that in series arm we have an inductor, and in the parallel arm we have the capacitor. Whereas in Cauer 2 form of LC networks, we have capacitor in the series arm and inductor in the parallel arm. I hope everybody is able to identify the difference between the two forms. So it may be a bit confusing, but you need to memorize the representation of Cauer forms of LC network. Okay. So on the left hand side of the slide, you can see that this is a generalized representation. So since this is series arm, we show it with the help of an impedance, and your parallel arm is shown with the help of admittance. Okay. So this is represented as Z1 as, this is Y2, that is admittance, then again impedance, admittance, impedance, admittance. This is how things proceed further. Okay. So next. So first, let us talk about the LC network synthesis for Cauer 1 form of LC network. So first we've discussed exclusively Cauer 1 form. So as we had discussed earlier in the previous class also, that one of the properties of LC network was that uh, the network function is represented as the ratio of the even power to the odd power. So same thing I have again shown you here, that ZS is equal to the ratio of even powered polynomial in the numerator to the odd powered polynomial in the denominator. Okay. So here you can see that your n is even and your m is odd. So in the numerator, we have an s raised power n, then an minus 2 s raised power n minus 2. So you can see there is a gap of 2. That means these are your even power terms. Okay, so if n is 4, then this will be 2 and so on. Similarly, here, if m is, say, for example, 3, so this will be m minus 2, that is 1. So we have here odd power terms in the denominator. And this ZS is nothing but your driving point impedance. I hope all are able to appreciate this network function, that is your driving point impedance. Now, this driving point impedance we will represent in a different way. Okay, different way in the sense that, as we have talked about very frequently in our network synthesis procedure, that we are using long division or we are using continued fraction approach. Okay, so uh, in this continued fraction approach, we will be representing this ZS in the form of, you can say, Z1 Y2, like that. Okay, so first what we are doing, uh, the generalized representation of your driving point impedance, we are doing that in the form of continued fraction. How are we doing that? See, we know that in case of your uh, impedance, your impedances, they are simply added in series. Okay, and when things are in parallel, in case of parallel networks, your admittances are simply, you can say, added. Okay, and if you remember the procedure that we had discussed in the previous class for Foster forms, there I had told you that, like, first we will segregate the impedance part. Okay, and then we will invert the remaining part. Okay, and then we will try to solve that. Okay, see, this is what we had shown in the previous class, that we had Z1 plus Z2. So what we did, we identified Z1. Then for identifying the remaining part, what we did, we obtained inverse. In a way, inverse in the meaning that, like, Z2 is shown as 1 by Y2. So these two expressions are exactly same, but we are representing Z2 in the inverted form through its admittance. Okay, so same thing we are doing here. You can see that ZS is Z1S plus. Okay, now we have parallel arm. So your parallel arm will be represented as 1 by this one, Y2. Okay, now since our network is continuing, so what we are doing, Z1 plus 1 by Y2 plus, okay, then series has come. So again inversion, and we will have 1 by Z3. So what we have, 1 by Z3 plus 1 by Y4 plus 1 by Z5. So we are continuing that. First Z1, then Y2, then Z3, then Y4, then Z5, and so on. So this is the representation of your continued fraction approach. Now what we will do, you look at the figure number 2 in your slide. Here what we have done, since we are discussing Cauer 1 form, so in Cauer 1 form, we have in the series arm the inductors, and parallel arm consists of capacitors. Okay, so now what happens, what is Z1? Z1 is impedance. Impedance representation for inductor will be LS. Okay, so now you see here, you correlate this representation with this. What is Z1? L1S. What is Y2? This is Y2. So admittance for the capacitor is C2S. So we have C2S. What is Z3? L3S. Okay, what is Y4? C4S, and so on. So you must, understand these representations and correlate these generalized representation with the help of your inductors and your capacitor. So if you remember this, then it will be a very simple job for you to synthesize your LC networks through Cauer forms. Okay, I hope all of you have understood this thing. Fine. Let us now move forward. So here we discuss the different steps for realization, that in case of Cauer form, cover one form of LC network, which steps we have to follow. So I have jotted down these steps here, and let me tell you, these steps are though given in the book, but not exactly in the same fashion as I have shown you. I have tried to present you the things in a way that you will be able to understand clearly. Okay, so if you follow these steps, you will at once be able to realize your cover one form of LC network. So please listen to these steps carefully. And also I'll advise that once my class is over, then after giving a reading to the book, you again go through my video lecture, so that you are able to concretize your concepts. Okay, so step number one. So your step number one will be, we have been given the driving point impedance function. Okay, where in the numerator we have even powered polynomial, and in the denominator we have odd powered polynomial. So first step that we have to do is, we have to arrange those powers in the decreasing order of powers. Okay, means first the highest power, and then it will keep on decreasing. Similar is the case with the denominator. So we have to arrange numerator as well as denominator in the decreasing order of powers. Fine. Now n is our numerator and m power is your denominator. Then what we have to do here, in case of Cauer forms, we have to identify the first element of the network and the last element of the network. Okay, so first let us identify what will be the first element. So in order to identify first element of the network, we have to check the value of n and m. N means the power of numerator, power of s in numerator, and m means the power of denominator, or degree in fact. Okay, so if the power of numerator polynomial or degree of numerator polynomial is greater than degree of denominator polynomial, then we will straight away say that our first series element will be an inductor. If this is not the case, that means the power of numerator polynomial is less than the power of denominator, then there will be no series element, and the first element will be shunt element, that is your capacitor. What I want to say, you look at this network, which is Cauer one form of representation. So here what is happening? We have an inductor, we have a capacitor. So first inductor is L1, first capacitor is C2. Okay, in case you are given driving point impedance function, in that function, if the power of numerator is greater than denominator, then we will have the first element as inductor. On the other hand side, if this is not the case, that is your numerator is having power lesser than your denominator, in that case inductor will not be present, your first element will be capacitor. This is how what we will have. So in case n greater than m, okay, then we will have such kind of Cauer one form. If your numerator is having lesser power than denominator, then we will have such type of network. Okay, so here you see that the first element is capacitor, we have removed inductor from the starting point. Okay, and here inductor is present. I hope this thing is clear to everyone. It is very, very clear. Next. So after we have identified first element and first series element or shunt element by looking at the powers of numerator and denominator, next step will be to obtain continued fraction. That is your long division that we discussed in the previous classes. So we will obtain continuous fraction operation for ZS. Okay. And after we have done that, our next step will be to determine the last element. Okay. Now you see, say this is the final portion of your LC network in Cauer one form. So here in this final portion, you may have both inductor and capacitor. You may have only inductor. Okay, so that thing you will have to basically find out by your network function. Okay, how can we do that? See, we will substitute in our driving point impedance function or your network function S as 0. Means if S tends to 0, then we have to check what is the value of ZS. So for S tending to 0, if ZS is equal to 0, then last element will be inductor. See, this will be the case. Means there will be no capacitor, no capacitor. We have removed the capacitor. We have shorted the capacitor. Okay, this will be the case for this. That is S tending to 0 and ZS 0. Both are 0. If both are 0, then last element will be inductor. Fine. Then another case. If we make S tends to 0 and our impedance function value is infinity for S tending to 0. In that case, last element will be capacitor. See, inductor is already there, but last element capacitor has come. Okay, so this is the determination of the last element of the your Cauer 1 form of LC network. That's it. So this is the procedure for your Cauer 1 form of LC network. Firstly, we will identify the first element. How will we identify first element? By looking at the powers of n and m, and very easy, if n is greater than m, your first series element is inductor. Otherwise, inductor will not be there. First element will be shunt capacitor. Next, what we will do the long division or your continued fraction operation for ZS. After we have done that, we will determine the last element. For last element, we will make S tends to 0. For S tends to 0, if ZS is also 0, we will have an inductor. Means if both are 0, we have an inductor. If both are not 0, that is one is 0 and another is infinity, we have last element as capacitor. Okay, I hope everybody has understood this. So students, after discussing these steps for realization, now we move to example for that. So this is the numerical example for Cauer 1 form. You see, we have been given with the driving point impedance function. Okay, so here you see in the numerator we have odd power terms. Okay, power is 5, 3 and 1. In the numerator we have even power terms. So see, it is not mandatory that numerator will always be, you know, even, or denominator will always be odd. It can be other way around also, either way. So in case of LC network, the ratio of your network function is odd to even or even to odd, whatever. Fine. So here see, first we have to identify the first element. So for first element, we will see whether numerator is greater than denominator or not. So here we find that numerator is greater than your denominator. It means we will have inductor as the first element. So this we have already identified. Now second step will be the long division. That is your continued fraction approach. So what we do, we put numerator as your dividend, then your denominator as your divisor. So what we do, we divide. So for division, your quotient will be s. So we get s raised to power 5 plus 3s cube plus s, and you have to subtract. So if we subtract, 3s minus s will be 2s, 5s cube minus 3s cube will be 2s cube, and s5 s5 these will be cancelled. So now this remainder becomes the divisor for next division, and your this divisor, it becomes the dividend. So now we will again divide. So we have S4 here, we have S3. So, and basically what we do, we try to match the first term in this division, or the highest order term in this division. So since this is 2s cube, this is S4. So for this we have to bring S4. So for S4, we have to divide by 2 and multiply by S. So means S by 2. So if you multiply this divisor by S by 2, so we get S4. And फिर S by 2 multiply with 2S gives us S square. So if you subtract, what do we get? This S4 will be cancelled. We get 2S square and this 1 as it is. So now this is our remainder, which becomes divisor. So we have brought it here. Okay. So this is our divisor. Dividend is the, this divisor has become the dividend. Okay. Now we again divide. Quotient is S. We again subtract. So this term is cancelled. 2S minus S is S. This again comes here. We get 2S square plus 1. So with 2S, we get 2S square. Then we get 1 as remainder. We have S, then S. And finally, we get 0. It means our continued fraction is over. Okay. So we have to keep on doing continued fraction till we get 0 at the end. Okay. So we have now concluded with our second step, that is your continued fraction. Fine. Now let us move forward. So after doing continued fraction, let us see what we have got as the quotient. You have to identify the quotients. First quotient is S, then we have S by 2, then we have S, then we have 2S, then we have S. Okay, and these quotients are these, these components only. Like this is the first component. You can say this Z1S is S, Y2S is S by 2, Z3S is this S, Y4 is 2S, Z5 is S. So very, very simple. Okay. And I have already told you that how will we represent this network through, continued fraction mathematically. See, this was our impedance function. This is how we have represented. This is Z1. I told you Z1. After Z1, what we will have 1 plus Y2, 1 by Y2. So we have 1 by, this is Y2, plus 1 by Z3, then plus 1 by Y4. Okay, and so on. So those Z1, Y2, Z3, we have replaced by those quotients of our continued fraction. Okay, let us see. It will be clarified in the next slide. See here. So what we have, this is our earlier representation. Okay, and here Z1 is nothing but your S, then your we have C2S like this. Fine. So now let me go back to previous slide first. After doing continued fraction approach, I told you that our next job will be to identify the last element. So for last element, what we require, we need to make S tending to 0. And we have to check what will be the value of ZS. You see here, if you make S tends to 0, then this will be 0. This will be 0, we'll be left with 1. And in the numerator, we have everything 0. So we have 0 by 1. 0 by 1 is nothing but 0. Means for S tending to 0, our ZS becomes 0. Fine. It means the last element will be inductor. I told you when both are zeros, we will have inductor as the last element. So we have first element as well as the last element, inductor only. Fine. So now let us see. This is what we have represented. This is what? L1S. Okay. So L1S is nothing but value of L1 is 1 Henry. What is this? You see here, this is C2S. C2S is S by 2. What is the value of C2 then? 1 by 2. Then L3S. What is L3S? S is there, L3 is nothing but 1. So L3 is 1 Henry. Then we have C4S. So what is C4S? 2S. So value of C4 will be 2. After C4S, what will come? We'll have L5S. Okay. So this is 1 by L5S. Fine. So what will be the value of L5 then? L5 is nothing but 1. Okay. So that is our Cauer 1 form. So how do we represent Cauer 1 form? L1, its value is 1 Henry. Okay. Then C2 is 1 by 2 Farad. So this value is 1 by 2 Farad. What is L3? 1 Henry. So this is will be 1. Then what is C4? C4 is 2. What is L5? That is your 1. And this is nothing but your Cauer 1 form of LC network representation. I think very simple thing, and all of you have clearly understood Cauer 1 form of realization, network realization for your LC network. Okay. So students, after Cauer 1 form of representation through numerical example 1, now we move to Cauer 2 form. So this is your Cauer 2 form of LC network. So first we have to identify what is the difference between Cauer 1 and Cauer 2. Though I have already told you about Cauer 1 and represented Cauer 2 also. So in Cauer 2, your series arms that will have capacitors, and your shunt arms will have inductors. Okay. Now, in case of Cauer 2 form of LC network, the driving point impedance, it is represented like this. I hope you are able to make out the difference between the representation of the driving point impedance. If you look at this driving point impedance function carefully, in case of Cauer 1 form, we had represented our network function in the order of decreasing power. Whereas here we have represented our network function numerator and denominator in the order of increasing power. See, in the numerator we have A naught, then A1S, then AN minus 1, SN minus 1, AN, SN. See, the power of S is increasing. Whereas in Cauer 1 representation, the power of S was decreasing. Similar is the case in the denominator. So there also the power is increasing, S raised power 1, S raised power 2, S raised power n, like this. Okay. And this is one difference. Another is the same kind of representation. If you represent your driving point impedance through continued fraction, how can we do that? This is the same one. Like we have Z1, then plus 1 by Y2 plus 1 by Z3 plus 1 by Y4 plus 1 by Z5, and so on. Now, in what way difference has come? Earlier, our Z1S was L1S. Okay. Now, this is our Z1S, that is capacitor. So the impedance of capacitor is nothing but 1 by CS. So now instead of LS, we have 1 by CS. Now, what is Y2S? Y2S is, here we have inductor. So admittance for inductor will be 1 by L2S. So this is 1 by L2S. Okay. So your Y2 is 1 by L2S. What will be Z3? Z3 will be 1 by C3S. This is Z3. Then plus 1 by Y4. Okay. What is Y4? Y4 is 1 by L4S. This is 1 by L4S. And so on. Okay. So if you memorize these representations, general representation of your Cauer 2 form of LC networks, then very easily you can write this continued fraction approach. Okay. Now let us move to the steps of synthesis of Cauer 2 form of LC network. See, the first step is we have to arrange the polynomials of the network function or the driving point impedance function in the increasing order of powers. Okay. Then after we have done that, in the Cauer 1 form, we had checked the degree of numerator and the denominator. So here, instead of degree, we will check the order of lowest order term. Lowest order means this A naught and B1S. These are the lowest order terms. So here you see the order of denominator is higher here in this case. Okay, so we have to check if the lowest order term in numerator is less than denominator. Numerator is less than denominator. In that case, your first series element will be capacitor. Means your capacitor will be present. Earlier we had talked about inductor was present. Whereas if the lowest order term in numerator is greater than denominator, अगर numerator में आपका जो power है lowest order का, if it is higher than denominator, then there will be no series element. Okay, means this series element will go away and will have only the inductor element present. So series capacitor is not present here. So I think you are now able to correlate clearly this cover 2 form with your cover 1 form. More or less similar things, only there is a bit difference in the procedure of the synthesization of this cover 2 form of LC network. I hope this thing is clear. There we were identifying the highest order terms, and here we are identifying the lowest order terms in the numerator and your denominator. Fine. So then next step will be your continued fraction, the way we did in the cover 1 form. And after we have done that, the final step will be to identify the last element. So for last element, if you remember, in cover 1 form, we had substituted s tending to 0. Okay. In cover 2 form, we will make s tending to infinity. Okay. So what we will do, we will make s tending to infinity. All of you must have studied limit chapter in your mathematics in your +1 +2, I think. That used to be a common chapter during your +1 +2. So if s tends to infinity, what will be the value of zs? I think that you can easily make out. So if s tends to infinity and zs tends to 0, okay, in that case, your last element will be capacitor. Okay. Whereas if s tends to infinity, zs also tends to infinity. Okay. If both are infinity, then your last element will be inductor. Fine. So we have to make s tends to infinity and check whether z is 0 or infinity, and accordingly we will decide whether inductor is there or capacitor is there. I hope everybody is clear of this. So if case, the first case is for your only capacitor present as last element. In the second case, we have inductor present. Okay. So now let us move to the example of cover 2 form. Let us see that. So this is your impedance function for which you have to obtain the cover 2 form of LC network. Okay. So what we have in the numerator, s raised to power 4 plus 4s square plus 3, 2s cube plus 3s in the denominator. So what is our first step? First step is to arrange the powers in the decreasing order. Okay. So this will be 3 plus 4s square plus s4, whereas in the denominator 3s plus 2s cube. Okay. So once we have done this thing, that is arranging in the decreasing order of the powers, we have to identify the first element. Okay. So what we identify? We identify the order of lowest order term. Okay. So for lowest order term, you can see here numerator is less than denominator. Okay. Numerator is less than denominator. Fine. So here for when numerator is less than denominator, what will happen? See, if numerator is less than denominator, first series element is C1. It means the actual cover form. So capacitor will remain present. Okay. Then next we obtain continued fraction. Continued fraction, what we have done, what is the denominator? 3s plus 2s cube. Then 3 plus 4s square plus s4 as dividend. Now here also a bit difference as we discussed in Cauer 1 form. You see here we will match the lowest order terms. In case of Cauer 1, we matched highest order terms. So here lowest order is 3s and this is 3. So if we have to match that, we have to divide 3s by s. So that's why our quotient is 1 by s. So if we do that, 3s by s becomes 3, 2s square cube by s, it becomes your 2 by s, 2s square. We subtract, this will be cancelled, we get 2s square, s4 as the remainder, then this term comes as the dividend. Now this is 2s square, this is 3s. So in order to match these, we have to divide this term by 3 by 2s. So what we have, this is 3 by 2s. So if you multiply 2s square with 3 by 2s, you get 3s. Then this gives us 3 by 2s cube. If you subtract, this term will be cancelled. And you get as remainder s cube by 2. And you continue like this. And finally, we identify the quotients. Quotient is 1 by s here, 3 by 2s, then 4 by s, then 1 by 2s. Okay, so these are the quotients for our continued fraction approach. And these quotients are nothing but these values, C1, L2, C3, L4. Let us identify those values. See, so we have already talked about numerator is less than denominator. So first element is the series capacitor, that is this one. Then the last element, since s tends to infinity and zs tends to infinity, the last element is inductor. Let us discuss a bit about this identification of last element. So how do we substitute the limit of s tending to infinity? So when we substitute limit s tending to infinity, normally what we do, we take maximum terms in the uh, division part. Okay. So what we do, in the numerator, we take s raised power 4 common. Whatever is the highest power now, we take that as common. What we are left with 3 by s4. Okay, in the numerator I'm talking about. Then we get 4 by s square, then plus 1. This is what we get in the numerator. In the denominator, what we get, the highest is s cube. We take s cube common. So if we do that, we get 3. We have s cube common, so divide by s square. Okay, plus 2. And now this s cube will be cancelled, and here power 4 will be cancelled. We're left with s only. Now what happens if you make s tends to infinity? What will happen? This 3 by s square, infinity is in the denominator here. So 3 by infinity is 0. This will be cancelled. This is 2. Now here 3 by s4, this will also be 0. Okay. 4 by s square, this will also be 0. Okay, but we have s in the multiplication, so s tends to infinity. So overall, the value of zs, it tends to infinity. So for s tending to infinity, zs tends to infinity. That means the last element will be inductor only. Fine, that is this one. So, and these are the quotients that we have already written. We will correlate these quotients with your ls and cs, and we will be able to identify the values of the elements. How do we do that? Let us see. So these are the values. So see here, the first is 1 by c1s. Okay, so 1 by c1 is s is equal to 1 by s. It means c1 is 1. So your c1 is 1 farad. Fine. Then 1 by L2S. 1 by L2S is 3 by 2S. It means L2 is 2 by 3. L2 is 2 by 3. So this value of L2 is 2 by 3. Fine. Then what we have, 1 by C3S. 1 by C3S is 4 by S. It means C3 is how much? 1 by 4. So we have C4 as 1 by 4. Fine. This will not be C4, it will be C3. Okay. So C4 is C3 is 1 by 4. Fine. Then we have 1 by L4S. This is equal to 1 by 2S. Okay. That gives us L4 is equal to 2. So this value is 2. That's all. So with this, we are able to represent a given network in the form of Cauer 2 form of your network representation. Okay. So students, with this, the Cauer 1 and Cauer 2 form of a network synthesis for LC network is complete. I hope all of you have understood all the things. Okay.